In the previous video, we've been talking about the weak topology. So we've been talking about a topology on a Banach space X generated by neighborhoods of that forms centered at a point X and of size epsilon, where you test the proximity to X on finitely many elements of X star. Now, if you work on the Banach space X star, you can do exactly the same thing, testing the proximity of a functional Y star to a functional X star by testing on finitely many elements of the dual, that is the bidual of the space you started with. But you could also reverse the role of X and X star, and you could say that you're going to be looking at neighborhoods of this form, where around a point X star and capital X star, you say that a element Y star is close to X star by testing on not elements of the bidual, but elements of the space itself, right? Use the pairing between X and X star rather than the pairing between X star and X double star. If you do that, then the corresponding topology is called the weak star topology, and we use similar notation as what we've used for the weak topology when discussing the weak star topology. Now, are those two topologies the same? Well, what we're going to see in the next proposition is that they are the same if and only if they are the same for the obvious reason that you're testing on the same objects, right? So if you can identify X with X double star, then there's no difference in this definition where you test against elements of X and the definition of the weak topology where you would test against elements of X star star. But that only happens in that situation. In general, what we have is that X can be identified with a proper subspace of X double star, and therefore we are testing here on fewer objects than if we were using X double star. And because we test on fewer objects, we have fewer neighborhoods, we have a weaker topology. Now, the advantage of a weaker topology is that more sets have a chance to be compact. And indeed, we're going to build up towards the proof of this theorem due to Banach and Alaoglu. And this theorem tells us that in any Banach space that happens to be a dual, so if it's X star for some X, then the closed unit ball, I'm going to use this notation to denote the closed unit ball as written here, will always be compact. So the weak star topology is weak enough to ensure compactness of the closed unit ball. And of course, if you're in the reasonably nice situation of what we call reflexive spaces, so X can be identified with this bidual, then the weak star and the weak topologies will be the same thing. So in particular, we'll have compactness in the weak topology of the unit ball of your Banach space, the closed unit ball of your Banach space. But that's not going to be true in general. So in general, for the weak topology, we won't have compactness, but we will always have compactness for the weak star topology. So let's start with the proof of this proposition and show that the two topologies coincide if and only if, well, they coincide for the obvious reason that they are literally the same because you test on the same objects. So let's first assume that the topological spaces X star with its weak topology and X star with its weak star topology coincide. And now I have to show that X can be identified with its bidual. The other direction is trivial. That's just a definition. So I'm assuming this. And now I'm going to take a element X double star of the bidual, X double star, so the dual of the dual. Okay, now this element is weak star continuous, just by definition of the weak star topology. Weak star continuous. Right. Now, what does that mean? That means that there exists a epsilon, well, as a particular consequences, and there exists a X naught star in X star. So there exists a certain neighborhood for the weak star topology, so something of that form, such that this neighborhood is included in the inverse image of the interval, say, -1, 1 by X double star, right? If it's weak star continuous, then it sends open sets to open set. So an open set will have to contain some neighborhood of that form. Right. Now I'm claiming that the kernel of this functional on which you're testing will always be included in the kernel of x double star. That's for every j. So in particular, I could take the intersection of all these kernel and they would be included in the kernel of x double star. Now, how do we see that? So let's prove that. So let's y star be an element of the intersection of the kernels of the xj's. Right. So what can I say about that? Well, it's in the kernel of the xj, so that is to say, xj paired with y star is 0 for all j in 1 to n, because of course when I say kernel of xj, I see xj as an element of the bidual, so I see it as a function from the dual to R, so it's acting on an element y star by the duality product. And so this is true. This is okay. This is true. And what we have is that we have that xj. Well, if it's 0, I could always multiply it by a non-zero element, and it would still, or even by a 0 element, and it would still be 0. So for every t in R, this will be 0, and you could add x0 star and subtract x0 star. That won't change anything. So this is 0, and that's definitely smaller than epsilon. So what I have now is that ty star plus x naught star has to be in this intersection of the kernel, and it has to be in v epsilon x0 star x1 xn. That's for every t real number. Okay, but now remember that this is included in x double star minus 1 of minus 1 1. So that is to say that x star star of ty star plus x0 star has to always be smaller than 1. But that in turns tell me that x double star of y star plus x naught star divided by t, let's say if I divide by t on both sides for a non-zero t, divided by t has to be smaller than 1 upon t for every positive t. And now you can send t to infinity, and this implies that x double star of y star has to be 0. So y star is in the kernel of x double star. Right, so we've proven that claim here. Now, we've proven that claim that the intersection of the kernel of xj is included in the kernel of x double star, and we're going to use that to prove something much stronger, the next claim. That is to say that x double star is actually in the span of the xj's, right? And because the xj's are all in x, that means x double star would be in x. So x is can be identified with a subspace of x double star just by acting on x star in the obvious way. But that will tell me that any element of x star, the a priori bigger space, actually is a linear combination of element of x, therefore can be identified with x itself. So this will conclude the proof. Right, so how do we do this? Well, we're going to define a map, let's call it capital F, from x star into Rn plus 1. And this map sends a element of x star to the vector where you first test this element x star on your x double star, and then you test it on the xj's. Right? So you have to interpret all of that appropriately, of course. This is using the pairing of x star with x double star, and this is using the pairing of x star with x, which you can then also identify with a pairing of x double star with x star by identifying this x1 with an element of x double star, right? That acts on x star exactly in this way. Okay, so I have a map here, and the Ambanic theorem, so this map from x star to Rn plus 1, I can use the Ambanic theorem in Rn plus 1. And then Ambanic would tell me that I can separate the point, single point 1, 0, 0, from the range of f, right? Separating a single point from that set, that closed set to R of f. So what does that mean? That means that there exists an alpha, and there exists a lambda in Rn plus 1 that defines my hyperplane, such that lambda inner product with the vector 1, 0, 0 is smaller than alpha, but lambda inner product with f of x star is greater than alpha for every x star in capital X star. Now, let's unpack that a little bit. This is really telling me that lambda 0, it's the first inner product, is smaller than alpha, which is smaller than lambda 0 times x double star x star plus the sum of the lambda j x star xj, j equal 1 to n. Right, now that's true for every x star in x star. So in particular, I could multiply my x star by t. I would still be in x star. So this is true for every x star in x star and for every t in R. And because it's true for every t in R, this can only be 0, because you can multiply by a t that's either positive or negative, so it has to be both positive and negative. So what we have is that lambda naught is smaller than alpha, which is smaller than 0, which is equal to lambda 0 x double star x star plus sum of lambda j x star xj for every x star. Okay, but now my lambda 0 is non-zero, so I can divide by lambda 0, and I get that x double star x star has to be equal to minus sum of lambda j divided by lambda naught, j equal 1 to n of x star xj. That's for every x star in x star. And so this is literally saying what my claim was saying here, that x star belongs to the span of dxj, and so it can be identified with a element of x, which concludes the proof. So it's time to prove a theorem about the weak star topology, and we're going to prove the following very neat characterization of separability. A Banach space is separable if and only if the closed unit ball of its dual endowed with the weak star topology is a metrizable topological space. So that's very useful in practice. More often than not, we deal with separable Banach spaces, and then you know that all of your questions regarding the weak star topology can be reduced to question about sequences using the metrizability of the topology. But it turns out to be a characterization, which is a neat relationship between topological properties for these weak topologies the weak topology is being obviously related to the linear structure of your Banach space, and another topological property for the norm, which is separability. Okay, so these two things are beautifully intertwined through this theorem. Now let's start with the first direction, which is the simplest. So I'm going to start by assuming that it's metrizable. So I'm going to have D a distance such that as topological spaces, this space is homeomorphic to this space, right? Now, if I have such a distance, I can define for all n, I can define neighborhoods un of 0 by saying these are the sets of x star, the unit ball, such that the distance of x star to 0 is smaller than 1 upon n. Now, if I have this homeomorphism, this means that this open set for the topology defined by the distance will have to contain a neighborhood, so will have to be open for the weak star topology, so they will have to contain a weak star neighborhood. So what we have is that for every n, I can find such a weak star neighborhood. So there exists at epsilon n, there exists a xn star in the unit ball, and then there exists a finite family xn1 till xn capital Nn in X, such that this weak star neighborhood here is included in UN. And now I'm going to further define Y to be the span of all this X and J running between 1 and n, and well, and I'm taking a union of that over all n in n. I'm taking a span of this. So, okay, so we will have proven that X is separable if we show that Y is dense. So I'm claiming that it suffices to show that Y perp is 0, because as we've seen, this would imply that Y perp is X, Y bar is X, hence X is separable. Because Y is countable. Okay, so we need to show that Y perp is 0. So how do we do that? We take a Y star in Y perp, and we have to show it 0. What can we say about such a Y star? We can say that Y star X is 0, I should call that Y, for all Y in Y. And in particular, that means Y star X and J is 0 for every n in n and for every j from 1 to n. But if that is 0, then in particular it's smaller than epsilon n. So that is to say that Y star belongs to the epsilon n x star n xn1 till xn n, which is, remember, a subset of un, and that's for every n. But that, so by the way, this implies that, in fact, this is equivalent to that, and this certainly implies this, and then this is equivalent to saying that the distance between Y star and 0, that is not equivalent, but it implies, because you included in un, that the distance between Y star and 0 is smaller than 1 upon n for all n. So, okay, take the limit as n goes to infinity, and this implies that Y star is 0, which concludes this first direction, some of the easy direction of the proof. If the weak star topology on the unit ball is metrizable, then the space has to be separable, and the dense subset that spans the space is the subset of all those elements in X that you use to define the neighborhoods inside concentric unit balls for the distance d around 0. Not unit balls, I mean balls of radius 1 upon n around 0. Okay, so that was one direction. Let's have a look at the other direction. Okay, so let's assume that X is separable. Right. So I'm going to take a sequence xj that is dense in Bx. I can do that if X is separable. So with that sequence, I'm going to define a new norm. So I'm going to define the norm, triple norm of X star to be the sum j equals 0 to infinity of 2 to the minus j times the inner product of X star with xj. Okay, so that's not too hard to show that this is a norm. You can leave that as an exercise. Is a norm on X star, and that norm is controlled by the standard norm on X star, right? For every X star in capital X star, you know, that's because these functionals here apply to xj, because xj is in Bx, so this is always smaller than the norm of X star, and sum of 2 to the minus j is 1. Right, so what we need to show is that the distance induced by that triple norm gives a topology on the unit ball of X star that is equivalent to the topology, the weak star topology. So for that, I need to show that if I have a ball for this triple norm, I can fit in a weak star neighborhood inside it, and reciprocally, if I have a weak star neighborhood, I can find a small enough ball for the triple norm inside it. Okay, so let's go with one inclusion. Let's give ourselves a neighborhood in the weak star topology. So an epsilon, a center point in Bx star, and some element of X against which we are testing. Right, now what do we want to do? We want to need to find a delta small enough to ensure that whenever in triple norm you're close to X naught, then you are inside this neighborhood V epsilon X naught star y1 till yn. Now what do we have? We have that for every j equal 1 to n, X star, so if we are in that ball, so for every X star in Bx star such that this triple norm is small, delta is to be determined later, we have that for every j, X star minus X naught star tested on Yj has to be smaller than 2j delta, right? That's because of the definition of the triple norm. If the triple norm is smaller than delta, you know, every element here has to be smaller than 2j times delta. And that's not yj, that's xj here. Okay, now it's xj, not yj, but I can find an xj sufficiently close to a yj. So because the xj, remember, are dense in the unit ball Bx. So and I should have said that without loss of generality, the yj I'm taking here can be taken in Bx, defining that neighborhood. So, okay, so I can pick j, let's call that j1 till jn, such that xjk minus yk in standard norm is smaller than epsilon. let's say epsilon over 2, right? That's by density of the xj, so I can approximate my yk by some xjk. All right, now I can choose delta. That's the one moment where we choose it. I can choose delta such that 2jk delta is always smaller than epsilon over 2 for all k equal 1 to n. So I pick it that small such that this would be smaller than epsilon over 2 and this is smaller than epsilon over 2. And now when I look at the x star minus x naught star tested on yj, let's call it yk, I can use triangle inequality, and this is smaller than x star minus x naught star tested on xjk. Xjk, yes, xjk itself, and then plus the x star minus x naught star tested on yk minus xjk. Right, now for the first elements, I can use that this is smaller than 2jk delta, and then 2jk delta is going to be smaller than epsilon over 2. And for the other one, I can use the fact that by definition of the norm on the dual, this is smaller than the norm of x star minus x naught star times times xjk minus yk. Right, but this norm x star minus x naught star is certainly smaller than 2 because x star is in the unit ball and x naught star is in the unit ball. So this is smaller than epsilon over 2 plus 2 times the norm of xj minus yk, which is also epsilon over 2, and that gives me 3 epsilon over 2, which is not what I wanted. So I need to pick that smaller than epsilon over 3. Right, and now this whole thing is equal to epsilon. Okay, and that shows one inclusion, right? We've shown that given any weak star neighborhood, I can find a ball for the triple norm that is inside that neighborhood. And how small need that ball be? Well, that small. I need to pick my delta satisfying this property that only depends on on this jk's, that depends on what the yk's were and which elements of the dense subset are close enough to them. Now for the other inclusion, this is a little simpler. I give myself a delta and I give myself an x naught in bx star, and then I want to find a weak star neighborhood that is inside the ball of radius delta centered at x naught star for the triple norm. So what does that mean that the triple norm is small? Right, so what is the triple norm again? Is the sum of the 2 minus j x star minus x naught star xj, j equals 0 to infinity. So you can split that in 2 and write that as the sum j equals 0 to n of 2 to the minus j x star minus x naught xj. And this being small is really a condition about being in a weak star neighborhood, testing against these finite xj's, j running between 0 and n, and then you have that plus the rest of the sum starting at n plus 1, and we're going to pick n appropriately in a minute. So for this term, I could control it by the sum of the 2 to the minus j times the norm of x star minus x naught star, which is at most 2. Right, so this entire thing is smaller than the sum j equals 0 to n of 2 to the minus j x star minus x naught star xj, okay, which is certainly smaller than, let's say, the maximum of these quantities for j running between 0 and n, because the sum of the 2 to the minus j is, did I start at 0 or did I start at 1? I started at 1. If not, the sum of the 2 to the minus j would be 2. So this maximum here, okay, the sum of the 2 to the minus j is 1, so this is controlled by the maximum. And here I have something that is controlled by 2 to the minus n. Now what do? I pick n such that 2 to the minus n is smaller than delta over 2, and then I pick epsilon smaller than delta over 2, and now I have that for every x star in V, actually pick epsilon equal delta over 2, in V delta over 2, x naught star, and then x1 until xn for that choice of n that we've made, this x star minus x naught star in triple norm has to be smaller than delta. So we've shown that inside the ball defined by this inequality, we have this weak star neighborhood, and that concludes the proof.